Good day and welcome back to the deep dive. This week, 3I Atlas reaches a geometry we've never seen before, and quite frankly, one that we might not see again for another generation of interstellar surveys. If you've been tracking the orbital parameters since perihelion, you know we've been waiting for the calendar to hit January 30th, 2026. That is the date just 8 days from now when the phase angle of this object collapses to an almost impossible 0.69 degree. We are talking about a near-perfect alignment between the Sun, the Earth, and the comet itself. This isn't just another data point in the ephemeris. This is the zero-phase alignment we have been theorizing about since detection. As of today, January 22nd, we are watching the angle narrow hour by hour. Most comets, the ones native to our solar system, are rarely observed at phase angles below 10 degrees due to orbital mechanics and safety limits for ground-based telescopes pointing near the Sun. Even our last interstellar visitor, 2I Borisov, frustrated astronomers by never dipping below 16 degrees during its observable period. It kept its secrets hidden in the shadows of its own surface roughness. But 3I Atlas is breaking that rule. Let's look closer at the data coming in from the high-precision photometry teams. We are looking at a window that opens on January 27th and stays open until February 4th. That is an entire week where the phase angle remains below 2 degrees. This is the surge window, and right in the middle on the 22nd, we hit that 0.69 degree minimum. This is the opposition surge territory, a region of optical physics where the rules of brightness change dramatically. Why does this specific angle matter? Because when you look at an object with the Sun directly behind your head, shadows disappear. Literally, every pebble, every dust grain, every fractal aggregate on the surface or in the coma hides its own shadow from your view. The result isn't just a linear increase in brightness, it's a spike, a non-linear dramatic surge in intensity that tells us things about the surface texture that no spectrum or standard image ever could. At the moment of this peak alignment, 3I Atlas will be roughly 3.33 astronomical units from the Sun and 2.35 astronomical units from Earth. We are projecting an apparent magnitude of V approximately 16.7. That is faint for the naked eye, but it is like a beacon for the 8-meter class telescopes and even the highly optimized smaller apertures equipped with precision photometers. They are all swinging into position right now. The observation schedules at Cerro Paranal and Mauna Kea have been wiped clean for this. If you're relying on the standard public feeds for these updates, you're missing the granular breakdown of the light curves. Hit that subscribe button now to make sure you get our nightly analysis as the data comes down from the observatories. We'll be tracking this magnitude spike in real time. The geometry here is critical. Ordinary comets don't give us this look. They stay sidelit or backlit relative to us. To get a frontlit view, what astronomers call opposition, usually requires a planet with an orbit outside Earth's like Mars or Jupiter. But 3I Atlas, with its hyperbolic high-inclination trajectory, is cutting through the plane in a way that lines it up perfectly with our sightline to the Sun. This is why the mood in the community is so tense. We aren't just taking pictures. We are waiting for a specific physical phenomenon to trigger. If the brightness spikes exactly as the angle hits 0.69 degree, it confirms we are seeing the opposition surge. If it doesn't, or if the curve is flatter than predicted, we have to rewrite our models of what this thing is made of. The fact that 2I Borisov never let us see this phase means 3I Atlas is our first true shot at understanding the microtexture of interstellar material. We have models for zodiacal dust. We have models for cometary dust from the Kuiper Belt, but we have zero observational data for the phase curve of an interstellar object at sub-2 degree angles until next week. So what does this actually mean for the observation strategy? It means instrument calibration is happening now. Polarimetry, measuring the polarization of the light, is going to be just as crucial as the brightness. As the phase angle drops, polarization usually goes to zero or flips. The way it flips tells us about the scattering properties of the particles. Are they singular grains? Are they fluffy aggregates? The 0.69-degree moment is the stress test for every theory we have published in the last 3 months. We know the trajectory is retrograde, we know it's inclined, but those represent the macro movement. The opposition surge gives us the micro-reality. It bridges the gap between seeing a dot moving in space and understanding the dust grain sitting on the surface of that dot. The clocks are ticking down. January 27th is the start of the less than 2-degree ingress. January 30th is the peak. This is precise, unforgiving orbital mechanics. There are no second chances with a hyperbolic trajectory. Once 3I Atlas moves past this alignment, the phase angle opens up, the shadows return, and the surge effect vanishes, likely forever for this object. We are about to stare directly down the barrel of a light beam reflected straight back at us from interstellar space. And the question everyone is asking is, how bright will the spike be? The answer depends entirely on physics we are about to discuss in the next report. But make no mistake, the zero phase is the main event of this entire encounter. As we established in the previous analysis, the window for the opposition surge opens on January 27th. But to understand why the scientific community is holding its breath for that 0.69-degree alignment, we need to strip away the astronomy and look at the raw physics of light. We are entering a domain dominated by two different mechanisms, and the distinction between them is the key to unlocking the composition of 3I Atlas. The opposition surge isn't a single phenomenon, it is a composite effect. And here is the crucial detail that makes next week's observation so high stakes. The surge behaves differently depending on the exact angle. First, we have shadow hiding. This is the intuitive part. Imagine a forest seen from an airplane. When the sun is directly behind you, you don't see the shadows cast by the trees because the trees themselves cover their own shadows. The forest looks brighter. This effect dominates when the phase angle is larger than about 2 degrees. Since 3I Atlas will be transitioning from larger angles down into the 2-degree zone, we expect to see this initial brightening first. It tells us about the macroscopic roughness of the dust, how lumpy the surface or the dust cloud is. But then we cross the threshold. Below 2 degrees, the zone 3I Atlas enters on January 27th. Something much stranger takes over. This is coherent backscattering. This is where the wave nature of light interferes with itself. When a photon enters a dust cloud, it bounces around, scattering off multiple grains before exiting. If the entry and exit paths are identical, which happens when the source, the sun, and the observer, Earth, are perfectly aligned, the light waves traveling these reciprocal paths interfere constructively. They amplify each other. Think of it like sound waves combining to create a sonic boom, but for brightness. This construct produces a narrow, intense cone of light directed straight back at the source. This is the brightness spike we are hunting for. This is getting deep into the photonics. So, if you have questions about the difference between scattering and reflection, drop them in the comments below. I'll pick the best ones for the weekend Q&A video. Why is this distinction vital? Because coherent backscattering only happens if the size of the dust grains effectively matches the wavelength of the light interacting with them. It is a direct probe of the microscopic structure of the material. If we see a sharp, narrow spike as we hit that 0.69 mark on January 30th, it proves that coherent backscattering is happening. That tells us the dust isn't just a solid rock. It's a complex medium of scattering particles. The amplitude, how high the spike goes, and the width, how quickly it drops off as we move away from 0.69 degree, map directly to the physical properties of the dust. We can solve for variables that are usually impossible to determine from a distance: mean free path of the photon, single scattering albedo. These aren't just buzzwords, they are the genetic code of the comet's coma. Ordinary comets are rarely observed at these angles, so our data set for them is sparse. But we have seen this effect on moons and asteroids and occasionally on Saturn's rings. But never, I repeat, never on an object that originated outside our solar system. This contradicts what we previously thought about our ability to analyze this object. We assumed we'd be limited to spectroscopy, guessing at chemical compositions based on absorption lines. But the physics of the surge gives us structural data. It tells us how the dust is packed. Is it a loose, fluffy, fractal aggregate, or is it a dense, compact grain? The packing density of the dust determines the width of the surge. A broad surge means one thing, a razor-sharp spike means another. Because we have 3I Atlas in this less than 2-degree channel for a full week, we strictly sample the coherent backscattering regime. We are effectively using the sun as a laser probe. We aren't just passively watching 3I Atlas, we are using the alignment geometry to perform an active experiment. The sun fires the photons, the comet scatters them, and because Earth is sliding into that specific 0.69-degree slot, we are the detector catching the interference pattern. If we see simple shadow hiding but no coherent backscattering, that is a massive discovery too. It would imply the dust grains are absorbing the light before it can scatter multiple times. It would suggest a material so dark and so absorbent that the constructive interference is killed off. This connects to the albedo question, which we have debated for weeks. Is 3I Atlas dark like coal or bright like fresh snow? The shape of the curve next week decides the winner. The models are running on supercomputers right now predicting the curve, but nature has a habit of breaking models. The physics of the surge is robust, but the variable is the interstellar dust itself. We are assuming it behaves like solar system dust, but what if the fractal dimension of interstellar aggregates is different? What if the grain growth in the interstellar medium produces structures that scatter light in a way we haven't parameterized? The physics is set. The geometry is locked. The only unknown variable is the material itself. And that brings us to the actual stuff 3I Atlas is made of and the clues hidden in that potential brightness spike. Building on the physics of the surge, let's talk about the dust itself. The brightness spike we discussed isn't just a flash of light, it's a fingerprint. The shape of that curve, specifically its amplitude, is going to settle the biggest argument in planetary science right now. Is 3I Atlas made of dark, carbon-rich gunk, or is it reflective, icy diamond dust? Here is the context. In our own solar system, comets are remarkably dark. The most famous one, 67P Churyumov-Gerasimenko, which the Rosetta mission visited, had an albedo of about 0.06. That is darker than fresh asphalt. It showed a well-measured opposition surge, which confirmed it was covered in this dark, porous, dehydrated material. So far, we have 0 well-measured opposition surges for an interstellar object. 2I Borisov was too far off angle. We have no baseline. 3I Atlas is the baseline. The amplitude of the spike depends on the albedo. If the dust grains are dark, dominated by carbonaceous material with a low albedo around 0.03, the multiple scattering of light is suppressed. Photons get absorbed before they can bounce around and interfere constructively. In this scenario, the surge will be weak, dominated mostly by the shadow hiding effect we talked about. It would confirm that interstellar comets are chemically similar to the primitive asteroids in our own outer solar system, dark, carbon-rich organic leftovers. But there is an alternative. If the grains are icy fragments with albedos of 0.1 to 0.3, the surge will be blindingly strong. Ice scatters light beautifully. A high-amplitude, coherent backscattering spike would tell us that 3I Atlas is shedding pristine icy material that hasn't been darkened by billions of years of cosmic radiation processing, or that the mechanism formed different kinds of crystals in the cold of the interstellar medium. This phase curve can also reveal the fluffiness of the particles. We use the term fractal aggregates. Imagine a dust bunny under your bed versus a solid pebble. Both might be made of the same material, but they scatter light differently. A fluffy fractal aggregate allows light to penetrate deep inside and bounce around, enhancing the surge. A compact grain reflects it off the surface. If 3I Atlas shows a sharp, narrow spike, it points to fluffy, porous aggregates. That would imply that dust formed delicately in a low-gravity environment and hasn't been compacted by collisions. It's the difference between a pristine snowflake and a hailstone. So what does this actually mean for our understanding of the universe? It gives us the first direct comparison between the building blocks of our solar system and the building blocks of another star system. If the microphysics of the dust matches 67P, it suggests a universality in star formation. It means the stuff of the universe is largely the same everywhere. But if the signature is radically different, say a hyper-reflective sharp spike or a completely flat line, it implies that the chemical or physical evolution of 3I Atlas's home system was distinct. Maybe it formed in a carbon-poor nebula. Maybe it's a fragment of a differentiated icy moon rather than a primitive comet. We are trying to decode the history of a star system light years away by looking at how a dust grain reflects sunlight here today. This is the detective work of astronomy. We can't fly a sample return mission to 3I Atlas, it's moving too fast. We can't land a rover. The opposition surge is our sample return. We are touching the dust with photons. New data suggests we should also be looking for polarization reversals. As we dip below 2 degrees, the polarization of the light should do a specific dance. If the dust is irregular and rough, the negative polarization branch typically seen at wider angles should minimize. If we see a deviation from that standard behavior, we might be looking at exotic grain shapes, needles, or plates, rather than rough spheres. This week is the test. The zero-phase alignment is the interrogation room. We have the suspect in the chair and the light is shining right in its face. If you are enjoying this deep dive into the microphysics of the cosmos, hit that like button. It helps the algorithm know you want more hard science and less fluff. However, there is another layer to this geometry. While we have been staring at 3I Atlas, analyzing its dust, 3I Atlas is in a position to stare back at us. And what it sees, or what an observer riding on it would see, is potentially even more profound than the dust itself. Given what we now understand about the alignment, let's flip the perspective. This is a mental exercise, but one with serious scientific implications. Imagine you are standing on the surface of 3I Atlas on January 30th, 2026. You look back towards the Sun. What do you see? You see the Earth because the phase angle is 0.69 degrees from our perspective. The reverse is true for the comet. From the vantage point of 3I Atlas, the Earth will almost transit the face of the Sun. It is an inferior conjunction of sorts. To a distant observer, Earth would appear as a dark silhouette or a tiny dot passing almost directly in front of the star. This geometry turns the Earth into an exoplanet transit target, and 3I Atlas is the observing platform. Why does this matter? Because we spend billions of dollars building space telescopes to watch distant stars, waiting for a planet to pass in front of them so we can analyze the starlight filtering through the planet's atmosphere. It's called transmission spectroscopy. We look for dips in specific wavelengths that indicate the presence of gases. Right now, 3I Atlas is in the perfect seat to perform transmission spectroscopy on Earth. If there were spectral instruments on that comet, they would be detecting the solar photons skimming through the upper layers of Earth's atmosphere. What would they find? They would see the spectral fingerprint of a habitable inhabited world. They would detect the great oxidation event signature, heavy lines of oxygen O2 and ozone O3. They would see methane CH4, which when found alongside oxygen, is a strong biomarker indicating biological activity. Neither gas persists long without life constantly replenishing it. But here's the crucial detail that makes this thought experiment chillingly real. They would also see technomarkers, chlorofluorocarbons, CFCs, industrial pollutants, complex molecules that nature does not produce in abundance. If an alien observer were sitting on 3I Atlas right now scanning the transit spectrum, the detection of CFCs would be the smoking gun of a technological civilization. The trajectory of 3I Atlas makes this possible. It is retrograde, moving opposite to the planets and inclined by only a few degrees to the ecliptic plane. This holds the object in the transit zone for longer than a highly inclined comet would. It is an optimal configuration for observing planetary transits. In this sense, 3I Atlas is an ideal platform. It's passing just a few astronomical units from Earth, 2.35 astronomical units to be exact, which is close enough for high signal-to-noise ratio, but far enough to see the system as a whole. This mirroring effect, us studying the comet while the geometry allows the comet to study us, highlights the reciprocity of the zero-phase alignment. We use the sunlight reflecting off the comet to potentially find ice or carbon. The comet uses the sunlight filtering through our atmosphere to potentially find life, us. This isn't just sci-fi speculation. Astronomers use these geometries to test our own ability to detect Earth-like life elsewhere. By analyzing the Earthshine reflected back from the comet, if we could separate it from the sun's glare, we can verify what a habitable planet actually looks like from deep space. It's a calibration for future missions like the Habitable Worlds Observatory. We are validating our own search methods. If we couldn't detect Earth's biomarkers from the position of 3I Atlas, we have no hope of detecting them on an exoplanet 100 light-years away. This alignment is a benchmark test for exoplanet science using Earth as the test subject. So 3I Atlas is doing double duty. It is a mystery to be solved and a mirror reflecting our own biological signature back into the void. As we move into the final days before the alignment peak, we have to appreciate the rarity of this setup: a retrograde orbit, a close perihelion, a low orbital inclination, and a timing intercept that puts Earth, Sun, and Comet on a single wire. The probability of this happening by chance with a random interstellar visitor is astronomically low. This improbable setup leads us to the final synthesis, viewing 3I Atlas not just as a rock, but as the ultimate interstellar laboratory.